how exactly or where exactly we need a spanning tree. Okay, so if I take a normal scenario, if I take a switch here, assume that I got some 40 devices. I got some 40 devices to connect in the LAN. So I got a switch which is a 24 port switch. So is it possible to connect 40 devices on a 24 port switch? In general, it is not possible to connect this 40 devices. So probably there are two possible solutions. Either I can go with another switch which is a 48 port switch, or what I can do is I can take another switch which is also 24 ports, and I can connect some of the users on switch 1 and some of the users on switch 2, and then I can extend the LAN, or I can extend the connectivity between the switch 1 and switch 2 by using a cross cable connection. Okay, so I'm not going to consider any VLANs or any other concepts here. Just assume that there is by default only VLAN 1. So this is how we extend the LAN, which means if you talk about any 200 devices, so probably there is no switch in general. We don't use a single switch which is going to connect all the 200 devices, but we are going to use some 8 to 10 switches which can be used to provide the connectivity in the LAN. So when you talk about 500 devices, also the same case applies. Okay, so in general, that's what happens. That's what we do. So we got 24 port switch, and we are connecting some users here and some other users here, and then we are connecting a cross cable connecting between the switches, which is going to extend the LAN. In case, what happens if this link fails? The link connecting between the two switches, if that fails, simple, the users connecting on switch 1 will not be able to communicate with the users connecting on switch 2, because the backbone link which is connecting between the two switches is down, or there is some problem with that. So to overcome this type of issues, what I did, I added one more link. So one more link means it is going to just cost you one cable, one cross cable, and maybe you need one extra port on both the switches to connect this one. So what I did, I tried to connect multiple links between the switches so that I can provide something called redundancy. I can get redundancy, so that I can get some redundancy here. So we're going to connect two links between the switches so that we can have some redundancy in between the links. So the good thing about this is it is going to provide me the redundancy. That's a very good thing. But the bad thing about this type of connection is it is also going to create the loops in my network. Let us see how it will create the loops. So by default, let's say there is a computer here who belongs to some VLAN. Okay, so any VLAN, so it is going to send a broadcast packet. Switches will do broadcast initially if the destination entry is not present in the MAC table, which means when this device sends a broadcast, the broadcast goes to each and every port of the switch, which means it will go to this port also. From there, it will go to the another switch. Again, whenever switch receives any broadcast packet, it will simply forward to all the ports, which means it will go to all the ports. Also, it will go to the other port which is connecting between the switches. From there, it will reach another switch. Again, from there, it goes here, and then it goes here, and then it goes here. So simply, it is going to create a loops. So we call this as broadcast storms. So broadcast storms are nothing but a continuous broadcast packets, and this broadcast will not stop. In order to make sure that this broadcast, either you have to remove the extra link, or you have to power off the switch, or your network is down. So there are only two things. So I just added one extra link so that I can have redundancy, and one broadcast packet is enough to make your entire network down. So this is the actual problem here with multiple links between the switches. So now what will be the solution now? Now we need to go with solutions. So one simple solution is remove the extra link. That is first solution I can say. Remove the extra link whichever you are connecting between the switches. Don't connect this one, just remove it. But I don't want to go with this solution because this solution will stop the loops it's okay, but it not provide me the redundancy. So I want to have a solution which can provide me both the options. So temporarily what you can do is you can shut down the extra link. That is one option here. What you can do is you can shut down the extra link, which means this extra link, whatever it is, I can temporarily shut down this link and it can use the alternate route. In case if this route fails, then automatically I can make it as no shutdown so that it can be used. That is one way of doing it, but it's really not possible to do it manually. Manually, can we do shutdown, no shutdown? Even if I shut down, if I do it manually, then I will never come to know when the main link fails. And when the user starts complaining, then I will realize that okay, the main link fails. I have to activate the backup link. And manually, also not a possible solution. This is not a possible solution. So probably we can go with alternate solution is I cannot go with this solution. I cannot go with this solution. I can go with, and it can also happen automatically also. And this automatic process is done by STP. So STP is a protocol which is going to identify multiple links between the switches. Like take an example, between the switches, I got multiple links. This is the first link, this is the second link, and this is the third link, this is the fourth link. So here I got 4 links between the switches. Assume that I got 4 links between the switches. So even if you have 4 links between the switches, STP will make sure that your first link is up and the remaining 3 links goes to blocking state. That's what we call as blocking state. Temporarily shutdown means we call that as blocking state, and the link which is in the forwarding we call as forwarding state. And in case if the first link fails, let's say the first link fails, it will automatically make second link up and automatically remaining will be blocking. In case if the second link also fails, it will make the third link up, but it will make sure that there is only one link running in the network. It will make sure that only one link at a time will work in the network. So which is going to again stop the loops. So no possibility of loops. At the same time, in case if that main link fails, automatically it will make the second link up. Automatically less than a minute, around 50 seconds time is the convergence time it will take to make your alternate link to up. So we'll see this practically also. We can verify this behavior. That's what we are going to see here. So this is the main job of STP. STP will make sure that it's going to stop the loops. That's what we learned just now. STP is going to avoid the switching loops which can happen between the layer 2 devices, especially when you are connecting multiple links between the switches. Okay, when you are connecting multiple links, this multiple links is going to create a problem for you. That is what data instability, continuous update of the MAC table, multiple frame copies, and broadcast storms. It was first developed by Digital Equipment Corporation. Later they made it as a standard protocol, and by default STP is running on each and every Cisco Catalyst switches. Now our job here is to make sure that understand how STP works here. So that is what we are going to see here, how STP is going to work in our scenario. So to understand this STP behavior, I am going to take a small scenario. So let us try to understand how STP works here. I am going to take a scenario here. I'll take my 3 switches, let's say switch 1, switch 2, switch 3. So here also I'm going to take 3 switches here, switch 1, switch 2, switch 3. So in these 3 switches, the first step, so here in this case, the first step here is they are going to select the root bridge. So the entire STP process goes in 3 steps. I can simply say the entire STP process goes into 3 steps. The first step is selecting the root bridge. The first step it is going to select the root bridge, and the second step is selecting the root port. Selecting the root port, and the third step selecting which ports should be in the forwarding, which ports should be in the blocking. In other words, we can say as designated ports, and the blocking ports are called as non-designated ports. So these are the entire process goes in 3 steps. That's what we are going to see here, how exactly it is going to do that. Okay, so to implement, either I can go through with the same steps, same switching technology. So let me try to open up if I have the same topology of switching here, STP. Okay, so here I got three switches here. You can say switch A, switch B, switch C. We'll come to practically verification, we'll see later on. So first we are going to see the behavior here. Okay, so now out of this three-step process, first let us start with the first process, that is selecting the root bridge. So root bridge means out of all the three switches, so in our scenario here I got three switches, and I want to find out that how exactly STP is going to stop the loops here, because if I take an example, there is a computer here, sends a broadcast packet, maybe this device want to send the information to this device, so it will go to this switch, and this switch will send back here, and it will come back here. So it is going to create the loops, and I want to understand how exactly the switch is going to stop the loops in my scenario, in this scenario here, how exactly it is going to work. So now the first step is selecting the root bridge. So out of these three switches, that is switch 1, out of switch 1, switch 2, switch 3, any one switch has to become the root nothing but master. Just like master, anyone has to become the root bridge. Root bridge means root switch. Bridges, switches or terms are interchangeable. If I say bridge means, you have to understand it's a switch only. So the first step, it is going to select the root bridge. Out of switch 1, switch 2, switch 3, anyone has to become the root bridge. But now the question is, who is going to become the root bridge, whether switch 1, switch 2 or switch 3. So that will be decided by the bridge ID. So whichever the switch is having the best bridge ID, that switch is going to become the root bridge. But now the question is, what is bridge ID? So bridge ID is a combination of priority value plus MAC address. In general, we call it as a base MAC address. So by default, it is going to consider the priority value first. In case if there's a tie in the priority value, then it will consider the MAC address of the switches. Like if I take an example here, in my device, in my setup, if I'm going to take three switches here, if I say the priority value of this device is 32768 of switch 1, let's say the priority value of the second device is 4096, let's say the priority value of this switch 2 is 8192. So out of these three devices, whichever the switch is having the least priority value, in case of spanning tree, least is the best. In case of spanning tree here, least is the best, least always wins here. So in our example, switch 1, switch 2, switch 3, switch 3 is going to become the root bridge because it is having the priority value of 4000 when you compare with 32,000 or 8000. So in case if a router come across a scenario where there is a tie in the priority value, like even you can come across scenario like 32768 is the default priority value on all the Cisco switches. In case if all the three switches have the same priority value, let's say there is a tie in the priority value, then the tiebreaker will be the MAC address. Each and every device, each and every switch will have its own MAC address. We call that as base MAC address. Even if you want, you can verify with a command called show version command. I got a command here, I can show you that. If I just try to open up my switches, command line of my switch, show version command will show you MAC address. We call that as base Ethernet MAC address. So it is a MAC address it is a MAC address of the device itself, the switch itself. It's not the MAC address of any other computer or any other device. It is the MAC address of the switch itself. In case if the switches comes across a tie in the priority value, then the tiebreaker will be the MAC address. In this case, let's say the MAC address of this device is 000000000001, let's say. So I'm just using some simple numbers, and similar way here the MAC address of this device 000000000003, and let's say the MAC address of this device is 0000, all zeros, and in the last I'm just using 2. So whichever the device is having the least MAC address, least means first you have to compare the first number. If the first number is same, compare the second number, like that you'll go on. You can see this is the least MAC address, so which means switch 1 is going to become the root bridge. So in our example, this is going to become the root bridge, and the remaining switches, whatever the remaining switches, these switches will become as non-root bridge. Generally we call all the remaining switches as non-root bridges. Okay, so the first thing, selection is done, elections, and election is done based on bridge ID value. Bridge ID is a combination of priority value and the MAC address. First it will try to see the priority value. In case if there is a tie in the priority value, then the tiebreaker will be the MAC address. So here also I got some 3 switches here. So out of these 3 switches, any one switch is going to become the root bridge. So I want to take this diagram one more time. So let's say this is my switch 1 connecting to switch 2 and then connecting to switch 3. Okay, so this is how they are connected. Okay, so now the default priority value of this, all these devices are 32768. Also the device priority value 32768, which is default on Cisco switches, and 32768 here as well. So 32768 here as well. In case if there's a tie in the priority value, the tiebreaker will be the MAC address. Like I'm going to take some random MAC addresses. I'll take as 00100 1234, or I can take 1234 here, and here I can say 0010 and then 1111 and 1111, something like this. I'm going to take the MAC address, assuming the MAC address of this device is 1111 0000 and then 1111, something like this. So in this case, if you compare all the 3 MAC addresses, this is having the least MAC address when you compare with this one or this one. Okay, so which means out of these 3, any one is going to become the root bridge, which means switch 1 is going to become the root, and all the remaining switches will be referred as non-root bridges. Non-root means other than root bridge. So for each and every network, like any network if you take, even if you take an example of 20 switches in the LAN, by default there will be only one root bridge. You will be having only one root bridge, whereas all the remaining will be, some 19 remaining will be non-root bridges. All the remaining devices will be non-root bridges. So you will never have a more than one root bridge. So you always have only one root bridge, and all the remaining 19 will be referred as non-root bridges. In case if you assume that you have 20 switches in the LAN, one root bridge, remaining all non-root bridges. Okay, so now there is the first step which we discussed. Second step is, now coming to the second step. So first step, just now we discussed that the first step is selecting the root bridge, and the second step is selecting the root port. So root port is actually a shortest part of the root bridge. Like here you can see I got some definitions here. Root bridge, root port, the link directly connected to root bridge, or it can be the shortest part of the root bridge. So every non-root bridge looks the best way to go to the root bridge. For every non-root port there will be only one root port. Like the conditions here, like here also, every non-root bridge, like if you see the diagram here, every non-root bridge means here switch 2 and switch 3 are non-root bridges. Every non-root bridge looks the best way to go to the root bridge. So either it can go from here or it can go from here. Out of these 2 routes, this is the first route and this is the second route. Any one route can be the best. So, and whichever the port connecting to that particular switch, that port will be considered as root port. So either this port or it can be this port also. But out of these 2, any one can be the root port. So whichever is the shortest or whichever is the best one. So similar way, the same thing applies for other switches also. Like every non-root bridge, even this switch also will try to reach the root bridge. This is the one way, or it can go from this route also. Out of these 2 routes, first and the second routes, any one can be the best, and whichever the best, that particular port is going to become the root port, either this port or this port, depending upon the things depending upon the calculation. So in simple, every non-root bridge looks the best way to go to the root bridge. That is the second step. What happens? So now it's already decided that this is the root. So now everyone has to look the best way to go to the root bridge. So now the calculation. Now based on what factors it is going to see the best factors? Based on what factors? So first it is going to see the cost. First it is going to see the cost of the links. So cost, it is predefined depending upon the speed. If you are running 10 Mbps of speed, so anyway this original cost we don't use as of now. So probably this is what we use. If you are using 10 Mbps of speed, the cost is 100. If you are using 100 Mbps, the cost is 19. 10 Mbps, the cost is 100 or 64. 100, okay. 1 gig, the cost is 4, and 10 gig, the cost is 2. The higher the speed of the link, the lower the cost. It's opposite reverse, just like your EHRP or OSPF metric. So now in our example also, if I consider this example, every non-root bridge looks the best way to go to root bridge, which means in my example also every non-root bridge looks the best way to go to root bridge, assuming that each and every link is 100 Mbps link, assuming that all the links connecting between the switches are fast Ethernet ports and all are running 100 Mbps links. And in general, if they are running 100 Mbps links, mostly the cost will be 19 as per the table which we referred just now, 19. So now if I go from this side, this route is having how much cost? The cost is 19. And this switched 3, if it goes from this side, the cost is 19 plus 19, 38. So from this side the cost is 19, and from this side the cost is 38. So which one is the least? So this is the least, which means this particular port is going to become the root port. So this port is the shortest part of the root bridge. The same thing applies for the switch 2 also. Switch 2 also will do the same thing. If switch 2 goes from here, so this will be considered as root port. So I'll simply write as root port this one. And the same thing, switch 2 also will do the same thing. If it goes from here, the cost is 19. The cost is 19 here. And if it goes from here, the cost is 19 plus 19. So it becomes total 38. So out of these two, which is the least? So this is the least. So which means this particular port is going to become the root port. So like that, if you have 10 switches, every switch will have one root port. So similar way, like if you have 20 switches, one root bridge, remaining all 19 root ports. Similar way, every non-root bridge will have one root port, which means in your network you will have 19 root ports if you assume there are 20 switches. The root ports are not present on the root bridge, but it will be present on each and every non-root bridge. So now even you can come across a scenario where there may be a tie. Even you can come across a scenario where there may be a tie in the cost also. Like if I take another scenario, like if I draw one more scenario here, let's take an example. This is my root bridge. This is actually my root bridge, I can say. It is actually connecting to some two different switches, and then it is connecting to another device here. Assume the MAC address of this device is 2C, the MAC address of this device is 2D. So now I need to decide which one is the root port, either this port or this port. So assume they all are 100 Mbps links, the cost is 19, 19, 19, 19. So if I go from here, the cost is 38. And if I go from here, the cost is also 38. So there is a tie in the cost. In case if the switches comes across a scenario where there is a tie in the cost, then the second condition is going to see, I got the condition. First it will try to see the cost, the MAC address of the switch ID. The switch ID, nothing but the bridge with the best switch ID, nothing but the MAC address of the forwarding device, I can say. So first it will see the cost, then the second condition it will see the MAC address of the forwarding switch. So in this case, the MAC address of this device is 2C and the MAC address of this device is 2D, which means 2C is least. So this particular port will become the root port. And even there is a possibility that there is a tie in the MAC address also. Even there is a possibility that there may be a tie in the MAC address also. In that case, it will see the port number. Like when it will be tie in the MAC address is, like if you take an example, I got a switch here which is a root bridge, and I got both the links going on the same switch. So now if I see the cost here, if I try to consider the cost factor here, the cost is 19 plus 19, 38, and the other route is also cost is same. Second condition, MAC address of the forwarding switch. As of now, both the links are going from the same switch, which means there is a tie in the MAC address also. Then the third condition it is going to see is the port number. So even though you are using different same port, you're not going to connect on the same ports. Let's say 20 and 21 are the two ports. The least port will win here. So which means out of port number 20, 21, 20 will become the root port. So first it will see the cost. In case if there is a tie in the cost, the MAC address of the forwarding switch, that is the second scenario here. And in case if there is a tie in the MAC address also, then the third condition will be the root port. But definitely you will have only one root port, that is mandatory. So in our diagram, whatever a diagram I took here, 3 switches diagram, in this case there is no tie in the cost, so probably we don't need to consider the other calculation. But in case if it comes, and finally the last thing, it has to decide which port should be in the designated or forwarding mode and which port should be in the blocking mode. So that's the final decision to be taken here. So now it will decide the final decision based on some factors, like if I take here, so whichever the switch becomes a root port, whichever the switch becomes a root port, all the ports of the root port will be always in the forwarding. Root bridge will never block its ports, all the ports in the forwarding. And whichever the port becomes a root port, all the ports of the root bridge will be in the forwarding, and all the ports which are root ports also will be in the forwarding. And out of these two ports, this port or this port, any one port has to go into blocking state. So that again decided based on again the same factors. First it will try to see the cost. So the cost is same on both the links. Then it will try to see the MAC address of the, this time they will see the local switch. The MAC address of this device is 1111 and this is 0010. So least will win, which means higher value will be in the blocking state. So this port goes into blocking automatically. So now the user connected on sitting on this side, if you want to communicate with this user here, he has to use the route which is on the other side. So this is how exactly the spanning tree is going to work. Okay. Okay, clear? So let us just practically verify this behavior. Okay, so I'm going to take a same scenario, not exactly completely same. I got 3 switches. I'm going to connect these 3 switches with cross cables. I'm going to connect port number 20 on this side, and then I'm going to connect cross cable connecting between port number 21, and I'm going to connect port number 22 here. So you can see the ports are in amber color here, because if I go to any one of the switch and if I give a command called show spanning tree, you can see all the ports goes to listening state first. So listening state means where it is going to listen to the BPD messages. Okay, so you can see the ports goes into listening state here, LSN state. After some time you'll see the port goes to learning stage. Okay, learning stage, LRN. After some time you'll see the port goes to forwarding state. So by default, whenever you start the switch for the first time, now you can see it turns to forwarding, and then now it turns to green here. Because the reason is, whenever you start the switch for the first time, by default each and every port goes through listening and learning stages. Those listening and learning stages nothing but they're actually listening to the BPD messages to decide who is the root bridge. So now in our case here, so by default each and every port goes through listening state, goes through this learning stage. So whenever you start the switch for the first time, by default all the ports will be in the amber color because it has to go through with listening state for 15 seconds and learning stage. So in the listening and learning stages, they are going to decide who is a root bridge by sending the BPD messages. So there are something called BPD messages. We call them as bridge protocol data unit messages. So these are the hello messages which are sent by switches for every 2 seconds. In general, the root bridge will send the BPD messages, and the date time is 20 seconds. So if there is no BPD messages for 20 seconds, in that case the switches will automatically understand that particular route or the link is down. And whenever you start the switch for the first time, by default every port of the switch goes through listening and learning stages. You can probably verify this by giving a command called show spanning tree. And in this listening and learning stage, it is going to decide who has become the root bridge, and then what are the root ports, of any non-root bridges, and which port in the forwarding, which port in the blocking. And by default, when it is in the listening and learning stages, it is not going to forward any traffic to any user in the network, because unless and until it decides and confirms that there is no possibility of looping. So that's what exactly it will do in the listening and learning stages. It's going to trace the multiple links between the switches and make sure that in case if you have multiple links between the switches, it is going to make any one of the link automatically to blocking state depending upon the different stages, like the same calculation what we discussed. So if you want to verify, you can verify this diagram here. You can see one of the port here, you can see it is still in amber color, which means this particular port is actually in a blocking state. You can see it is in the blocking state here, alternate port going to blocking. And when you show spanning tree, you'll see some outputs here. So you'll see something called root ID and bridge ID information. So root ID is going to say who is the root bridge, information about the root bridge, and bridge ID is going to give the information about a local switch. Root ID means whoever is the root, and the priority value of the root bridge is how much? 32769. So by default it is 32768. It is going to add 32768 plus VLAN number. So there is only one VLAN, that is VLAN 1. So that's the reason we say priority value is 32768 plus VLAN number. So that's the reason you'll see here 32769. So we call this as extended priority value. So it also includes the VLAN number into the priority value. And this is the MAC address of the switch who has become the root bridge. Right now my MAC address is different and the root bridge MAC address is different, which means the root bridge is someone else. Maybe the switch A, I don't think switch A, maybe I think switch B is the root bridge. So let us check switch B. So I'm going to switch B. This is my switch B. I'm on switch B. Just for clarification, you can use some name as B, and I can say show spanning tree. You can see this message, this bridge is the root. So this bridge is the root. This message indicates that this particular local switch has become the root bridge. And if you try to verify the MAC address of the root bridge and the MAC address of your local switch, both remains the same. And probably you'll see this message, this bridge is the root on only the switches whichever has become the root bridge. So out of these three switches, B has automatically selected as a root bridge because the MAC address of anyway priority value is same on all the switches. So the MAC address is the tiebreaker here. You can see the MAC address of this is 0007 ECCD and AC82. Okay, it's the same on both the sides because it's the same local switch. If you want to verify, you can go to other switch 0007 and the MAC address of this 00D0. And now here you can see the remaining ports. Like if I go with switch B, all the ports of the root bridge will be in the forwarding. You can see forwarding ports, and they are designated ports, forwarding ports. And this is the actual priority, port priority. We call this a port priority. Default is 128. Okay. So now what I'm going to do is these are our timers, the default hello timer and dead timers. I'm going to shut down this link, any one of the link. Assume this link fails. I'm going to switch B and I'll try to shut down this link, F0/20 shut down. Assuming that this link fails, So automatically this particular port has to come to forwarding, right? It will take some time because it will not come to forwarding automatically or immediately. It is going to stay back in 20 seconds in the blocking state. You can see still it is in blocking state. I'm just repeating the same command after some time you'll see this particular port turns to listening state. Now you can see this particular port turns to listening state because it is expecting some BPD messages from the root bridge on this side, but it's not receiving from this side because this particular link is down. So whenever it doesn't receive these messages, it will try to wait for 20 seconds, and then after some time it will go to learning stage, and then finally this particular port automatically turns to green, you can see here, because this route is down. Now this particular port goes to forwarding now immediately after 50 seconds. So the default timer, whenever any main link fails, let's say if the link fails, by default it will take around 30 seconds for convergence. So if the blocking port comes to forwarding, it will wait for 20 seconds for blocking state, and 15 seconds for listening, and 15 seconds for learning. So total it will take around 50 seconds time to converge or to use automatic backup link. Suppose if I make this main link comes back, let's say in my example again, what I'll do is I'll try to make sure that this link comes back again. So how to make it back? Again, you can give no shutdown command, and once I give no shutdown command, again if I go to this switch, on the switch this port again goes to blocking, this one again goes to blocking, and this will come to forwarding automatically after 30 seconds, because no single port will go to forwarding immediately unless and until there is a listening and learning stages. So every port before it goes to forwarding, it will go through listening and learning stages, then only it will go to forwarding. So you can just demonstrate a simple connection. You can have a simple connection between 2 or 3 switches where you can add multiple links, or if you want you can add some 4 or 5 switches also, which again makes more complicated. So probably you can try with 2 or 3 switches, and you can verify how exactly spanning tree is going to behave, and you can compare this priority value and the MAC addresses. And even if you want, I can give you some information, like if you want to change the priority value, this is the command you have to use: spanning tree VLAN 1 priority, and it should be given only multiples of 4096, which means if you give 4000, it's not going to accept. It will only accept anything multiples of 4096. In case if you want to make a specific switch as a root bridge, in that case you can even change the priority value. Probably you can try these options by changing some priority value and all those things. Okay. So mostly in our next sessions we'll see some more in detail of advanced spanning tree options like rapid spanning tree and all those things. Okay.